And you can review in your book with me, or you can just listen to this and take notes, however you want to do, whatever works best for you guys. Okay. So let me make sure that everything is set up for you guys to be able to see. And like I said, I will break this down to probably 3 different videos for you to watch. Okay, so cardiac cells. Um, in general, I'm going to move this bar up here out of our way so you can see what's going on. Cardiac cells have either a mechanical, which is a contractual, so that's where the heart contracts, or an electrical, which is kind of like a pacemaker function. Mitochondrial cells are also called the working cells or mechanical cells, and they contain the contractual filaments, okay? So when these cells electrically stimulated, they slide together and cause myocardial cell contraction. Pacemaker cells are also referred to as conducting cells or automatic cells. They are specialized cells of the electrical conduction system, and they're able to form electrical impulses spontaneously and to alter the speed of electrical conduction. Okay. Automaticity, okay? It's the ability of the pacemaker cells to initiate an electrical impulse without being stimulated from another source, okay? Then you have what's called the excitability or irritability. It's the ability of the cardiac muscle cells to respond to an outside stimulus, okay? Conductivity is the ability of the cardiac cell to receive an electrical stimulus and conduct that impulse to an adjacent cardiac cell, okay? Then we have the contractility. It's the ability of cardiac cells to shorten, causing cardiac muscle contraction in response to an electrical stimulus. The heart normally contracts in response to an impulse that begins in the SA node. The strength of the heart contraction can be improved with certain medications like digitalis, dopamine, and epinephrine. Okay. Okay, so cardiac action potential. So let's talk about this. So think of your heart kind of like a battery, okay? So it looks like a battery. There's electrons, there's current, there's polarity, and there's voltage. So you see over here, there's a positive and there's a negative, just as in a battery. So let's talk about how in a battery energy is released. A battery has 2 terminals. One terminal is positive, like I said, and one is negative. Charged particles exert forces on each other, and opposite charges attract. Okay, so opposites attract, remember that. Electrons, negatively charged particles, are produced by the chemical reaction inside the battery. If a wire is connected between the 2 terminals, the circuit is completed and the stored energy is released. Okay? This allows electrons to flow quickly from negative terminal along the wire to the positive terminal. Does that kind of make sense? If no wire is connected between the 2, the chemical reaction does not take place and no current flows across, okay? Current is the flow of electrical charge from one point to another. Separated electrical charges of opposite polarity, positive versus negative, have potential energy. The measurement of this potential energy is called a voltage. Voltage is measured between 2 points. In the battery part, if you're talking about a battery, the current flow is caused by the voltage or the potential difference between the two terminals. Voltage is measured in the units of volts or millivolts. So if you look at the heart just as you would a battery, it kind of makes sense, okay? All right, cardiac action potential. So there's electrolytes, ions, and cell membranes. The human body contains electrolytes, which are compounds that break into charged particles when melted or dissolved in water or another solvent. Differences in the composition of ions between the intracellular and the extracellular fluid compartments are important for normal body function, including the activity of the heart. Body fluids that contain electrolytes conduct an electrical current in much the same way as the wire in the battery, okay? Electrolytes move about in your body fluids and carry a charge, just as electrons moving along a wire conduct a current. So there's your comparison with your battery, okay? In the body, ions spend a lot of time moving back and forth across cell membranes. As a result, a slight difference in the concentrations of charged particles across the membranes of cells is normal. The potential energy, or the voltage, exists because of the imbalance of charged particles. This imbalance makes cells excitable. Okay, cell membrane pathways. So here you've got sodium, you've got potassium, you've got chloride, okay? Cell membranes contain pathways through which specific ions or other small water-soluble molecules can cross. So in this instance, sodium and potassium and then the chloride. All right. This looks like a lot, doesn't it? So kind of look, I think in your book you've got that on page 31, so you can spend a little more time and look at this, but here's some just examples of ion concentrations, different channels, and different transporters in a typical cell. Okay, so you've got your sodium and potassium pump over here. You've got potassium channels. So again, these are just all sorts of different pathways. Electrolytes are quickly moved from one side of a cell membrane to the other by means of pumps. These pumps require energy in the form of ATP when movement occurs against a concentration gradient. The energy expended by the cells to move electrolytes across the cell membrane creates a flow of current. This flow of current is expressed in volts. Voltage appears on an ECG, okay, as spikes or waveforms. Thus, an ECG is actually a sophisticated voltmeter. So again, these are all different pathways and ways for things to move, okay? Okay, so polarization or resting. When the inside of a cell is more negative than the outside, it is said to be polarized, okay? If you can see, it's more negative than the outside here. Okay, when a cell is at rest, potassium leaks out of it, okay? Large molecules such as protein and phosphorus remain inside the cell because they are too big to easily pass through the cell. So these large molecules carry a negative charge. This results in more negative charged ions on the inside of the cell. When the inside of the cell is more negative than the outside, it is said to be a polarized state. So let me say that again. When the inside of a cell is more negative than the outside, it is said to be a polarized state. Okay, so depolarization or stimulation, okay? Depolarization is the movement of ions across a cell membrane, causing the inside of the cell to become more positive. So it's the opposite. When opposite charges come together, energy is released. When the movement of electrolytes change the electrical charge of the inside of the cell from a negative to a positive, an impulse is generated. The impulse causes channels to open in the next cell membrane and then the next. The movement of charged particles across a cell membrane causing the inside of the cell to become more positive is called depolarization. Okay, so let me again state that. The movement of charged particles across a cell membrane causing the inside to become more positive is called depolarization. This must take place before the heart can mechanically contract and pump blood. Depolarization occurs because of the movement of sodium into the cell and proceeds from the innermost layer of the heart, the endocardium. So the very innermost layer of the heart is the endocardium, to the outer layer, which is the epicardium. Depolarization, which is an electrical event, must take place before the heart can contract, and the pump blood, which is a mechanical event. An impulse normally begins in the pacemaker cells found in the SA node of the heart. Okay? A chain reaction occurs from cell to cell in the heart's electrical conduction system until all the cells have been stimulated and depolarized. Okay, they all are going to get depolarized and stimulated. This chain reaction is a wave of depolarization. The chain reaction is made possible because of the gap junctions that exist between the cells. Eventually, the impulse is spread from the pacemaker cells to the working myocardial cells, which contract when they are stimulated, when the atria are stimulated. A P wave is recorded on the ECG. Okay, so when the atria are stimulated, a P wave is recorded on the ECG. Thus, the P wave represents atrial depolarization. When the ventricles are stimulated, a QRS complex is recorded on the ECG. Thus, the QRS complex represents ventricle depolarization. Okay, so the P represents atrial depolarization, and the QRS represents ventricle depolarization. Repolarization, again, resting. So repolarization is the movement of charged particles across a cell membrane in which the inside of the cell is restored to its negative charge. Okay, so you've got back here, I'm going to go back through this again real quick. So with polarization, it's when the inside of the cell is more negative than the outside. Okay. Depolarization is the movement of ions across a cell membrane, causing the inside of the cell to become more positive. And then repolarization is the movement of charged particles across the cell membrane in which the inside is restored to its negative charge. Okay, so on the ECG, the ST segment and the T wave represent ventricle repolarization. Okay, let me say that one more time. On the ECG, the ST segment and the T wave represent ventricle repolarization. So take note of that. Okay, some cardiac action potentials. Action potentials of fast response A and slow response B cardiac fibers. Okay, the phase of action potentials are labeled up above. The effective refractory period, or ERP, and the relative refractory period, RRP, are labeled again. So I want you to know that when compared with fast response fibers, the resting potential of slow fibers is less negative, okay? The upstroke, phase O, or phase 0, I should say, of the action potential is less steep. The amplitude of the action potential is smaller. Phase 1 is absent, and the RRP extends well into phase 4 after the fibers have repolarized. There are two main types of action potentials in the heart. The first type is the fast response action potential. It occurs in normal atrial and ventricle myocardial cells and in the Purkinje fibers, which are specialized conducting fibers found in both ventricles that conduct an electrical impulse through the heart. The second type of cardiac action potential is the slow response action potential. It occurs in the heart's normal pacemaker, the SA node, and the AB node, which is specialized conducting tissue that carries an electrical impulse from the atria to the ventricles. Okay, so this is the ventricle action potential. Current responsible for ventricle action potential. The length of the arrows show that the relative size of the ionic current, which is the equilibrium potential, or ECF, cellular fluid, or ICF, intracellular fluid, okay? The fast response action potential is divided into 5 phases. Phase O, or phase 0, is called the upstroke spike or overshoot, begins when the cell receives an impulse, okay? Then we've got, let me see here. Okay, so then the cells depolarize, cardiac contraction begins, the upstroke is followed by a period of repolarization, which is divided into 3 phases, phase 1, 2, and 3. And this is called electrical systole. During phase 1, which is the initial repolarization, the sodium channels partially close, slowing the flow of sodium into the cell. At the same time, chloride enters the cell and potassium leaves it through potassium channels. The result is a decrease in the number of positive electrical charges within the cell. This produces a small negative deflection in the action potential. The cells of the atria, ventricles, and the Purkinje fibers have many calcium channels. During phase 2, which is the plateau phase, calcium slowly enters the cell through calcium channels. Potassium continues to leave the cell through potassium channels. Phase 3, repolarization begins with a downslope of the action potential. Phase 4 is the resting membrane potential. This period is called the electrical diastole. Phase 4 is the sodium and potassium pump activated to move sodium out of the cell and potassium back in. Relaxation of the cardiac muscle occurs during phase 4. The cell will remain polarized until the cell membrane is reactivated by another stimulus. Okay. Cardiac action potential. So you can see here the phases. Okay. So make sure you kind of just look over this stuff in your chapters. Okay, refractory periods. The period of recovery that cells need after being discharged before they are able to respond to a stimulus, okay? So refractory period is the period of recovery. that they need after being discharged. All right, so there's absolute refractory period, ARP. Cells cannot be stimulated to conduct an electrical impulse no matter how strong the stimulus at this point. Relative refractory period, RRP, cardiac cells can be stimulated to depolarize if the stimulus is strong enough, okay? So here, ARP, absolute refractory cells cannot be stimulated. In the relative refractory period, RRP, cardiac cells can be stimulated to depolarize if the stimulus is strong enough, okay? So that's what you need to know there. Effective refractory period includes the absolute refractory period and the first half of the relative refractory period, okay? Again, includes the absolute refractory period and the first half of the relative refractory period. Subnormal period. Weaker than normal stimulus can cause cardiac cells to depolarize, okay? So in the supernormal period, weaker than normal stimulus can cause cardiac cells to depolarize, okay? All right, let's talk about the conduction system. We'll break it down pretty quick for you. All right, so in this, we have the the primary pacemaker, the SA node, okay, is the specialized electrical pacemaker cells in the heart are arranged in a system of pathways called the conduction system. In the normal heart, the cells of conduction system are interconnected. So the conduction system makes sure that the chambers of the heart contract in a coordinated fashion. So that's kind of what the conduction system does, is it makes sure that the chambers of the heart contract in a coordinated fashion. The normal heartbeat is the result of an electrical impulse that begins in the SA node. Although the SA node is the smallest electrical region of the heart, it is normally the primary pacemaker because it has the fastest firing rate of all of the heart's normal pacemaker sites. The built-in rate of SA node is 60 to 100, okay? 60 to 100 beats per minute. So that is the built-in rate. So remember that, please. Although the SA node normally fires at 60 to 100 beats per minute, this rate can increase to about 180 beats per minute, primarily through sympathetic stimulation. Okay, so the SA node, which is right there, if you can see that, is the primary pacemaker. Okay, and we have a built-in rate of the SA node, which is 60 to 100 beats per minute, but it can fire up to 180 beats per minute through the sympathetic system. All right, now the atria. So where would we find the atria? The atria is impulse leaves the SA node, spreads from cell to cell across the atrial muscle, okay? So the impulse is going to leave that pacemaker or the SA node, and it's going to spread from cell to cell across the atrial muscle. As the impulse spreads, it's going to stimulate the right atrium and the interatrial septum, and then it travels along a special pathway called the Brockman's bundle to stimulate the left atrium, okay? So SA node stimulates, it's a pacemaker, and then it leaves the SA node and it spreads cell to cell, okay? And then it is going to travel and spread, and it's going to leave, and it's going to go through the bundle to stimulate the left atrium is next, okay? This is going to cause a contraction in the right and left atrium, at the same time. Okay? Stimulated by the pacemaker in the SA node. Okay? Then it's going to leave the SA node. It's going to spread through the cells. And then it's going to stimulate the right atrium. And then it's going to stimulate the left atrium. And then this is going to result in a contraction in the right and left atria at the same time. Okay. So the AV node, supplied by right coronary artery in most people, delays conduction of impulse from the atria to the ventricles. Okay, so let's talk a little bit about that. The AV node is a group of specialized conducting cells that is usually located in the floor of the right atrium. Okay, so let's talk about that. AV node is in the floor of the right atrium, immediately behind the tricuspid valve. Conduction through the AV node begins before atrial depolarization is completed. Okay, so the AV node and the AV bundle. The AV node and the bundle is shown here, okay? And the organization of the AV node and the AV bundle, the numbers represent the interval of time in fractions of a second from the original impulse in the SA node. So the AV node has been divided into 3 functional regions according to their action, potentials, and responses. So let's talk a little about those 3. Okay. The AN node, or the atrionodal region, is also called the transitional zone, located between the atrium and the rest of the node. Okay. Then you've got the nodal region, or the N region, and it's the compact AV node when transitional cells merge with the mitonodal cells. And then you've got the NH area, or the lower region, where the fibers of the AV node gradually merge with the bundles of the HIS, okay? As the impulse enters the AV node through the internodal pathways, conduction is markedly slowed in the N area of the AV node, okay? So it's going to slow right there before the impulse reaches the ventricles. So it's going to slow right here in the N area before it goes to the ventricles. If the delay did not occur, the atria and the ventricles would contract at the same time. So we don't want that, so we want it to slow here, and that way they're not contracting at the same time. The delay in conduction allows both the atrial chambers to contract and empty all the blood into the ventricle before the next ventricle contraction begins. This increases the amount of blood in the ventricles, increasing the stroke volume. Some people have 2 or more conduction pathways, okay? So not everybody's the same. Okay, the conduction system. The bundle of HIS, or the AV bundle, connects AV node with bundle branches. Pacemaker cells in the NH area of the AV node have an intrinsic rate of 40 to 60 beats per minute. Conducts impulse to the right and left bundles. Okay, so we've got the different bundles here, okay, the right bundle branch and the left bundle. The left bundle will split into divisions called, fasciolus. Okay, so the right is thin and it travels to the apex of the right ventricle. The left bundle spreads the electrical impulse to the intraventricular septum and the left ventricle. The left bundle branch is thicker than the right. Okay, so the left is thicker than the right and splits into divisions. That's what you need to know about that. Okay, so these Purkinje fibers receive impulses from bundle branches, relay it to the ventricle myocardium, intrinsic pacemaker rate of 20 to 40 beats per minute. Okay, the right and left bundle branches divide into smaller and smaller branches and then into a fibrous network called the Purkinje fibers, which are above here. These spread out over the subdental cardial surfaces of both ventricles. These fibers have pacemaker cells that have an intrinsic rate of 20 to 40 beats per minute. Because this pacemaker rate is slower than that of the SA node and the AV junction, it is considered a tertiary pacemaker. Okay. Okay, conduction system summary. So let's talk, this is probably a slide that I would like you to really learn, okay? So let's learn what the intrinsic pacemaker beats per minute are, okay? So make a note of these. I would probably make notes somewhere. SA node, or the pacemaker mode, right, is 60 to 100 beats per minute. But remember, it can go up to 180, right? And then the AV node, we're not going to talk about that, but the bundle of HIS or the AV bundle is 40 to 60 beats per minute. And the Purkinje fibers is 20 to 40. Okay, so we kind of have a 3 different area pacemaker. Okay, SA node 60 to 100. The second one would be in the AV bundle, and it would be 40 to 60 beats per minute. And then the Purkinje fibers is 20 to 40 beats per minute. So please remember this summary. Okay. All right. Causes of dysrhythmia. So let's talk about that. So what's going to cause the heart to not be a nice, pretty, normal beats? Okay. What can cause it to be a little bit off? So what's going to cause dysrhythmias or abnormal heart rhythms? Result from disorders of impulse formation, disorders of impulse conduction, or both. Okay. So it can be a disorder of the actual impulse formation or the conduction, or it can be a combination of both. Okay, so abnormal automaticity, a condition in which one of the following occurs. Cardiac cells that are not normally associated with a pacemaker function begin to depolarize spontaneously. Okay, they're not staying with the rhythm. All of a sudden, spontaneously, they depolarize. Or a pacemaker site other than the SA node increases its firing rate beyond that which is considered normal. Okay. Usually, this occurs if cardiac cells that are not normally associated with the pacemaker function begin to depolarize spontaneously, like I said, or the SA node, something beyond the SA node is increasing its fire rate beyond normal. Okay, possible causes are ischemia, hypoxia, electrolyte disorders, and exposure to chemicals or toxic substances. Examples of rhythms associated with abnormal automasis include premature beats, accelerated idioventricular rhythm, accelerated junctional rhythm, and some other forms of tachycardia, ventricular tachycardia. Okay. Disorders of impulse formation, triggered activity. So abnormal electrical impulses occurring during repolarization when cells are normally quiet. So when a cell is normally quiet, all of a sudden we get an abnormal electrical impulse during the repolarization time, which is supposed to be quiet. Requires a stimulus to initiate the depolarization. Let's see, what can we say about this? So It occurs when the pacemaker cells from a site other than the SA node, okay, and myocardial working cells depolarize more than once after being stimulated by a single impulse. Some causes can be hypoxia, excessive catecholamines, MIs or injury, digitalis toxicity, and medications that prolong the repolarization. Okay. So conduction blocks. So partial would be slowed. All impulses are conducted, but it takes longer than normal to do so. Intermittent, some impulses are conducted, or complete, no impulses are conducted through the affected area. A blockage or impulse conduction may be partial or complete, okay? This can be, a block may occur because of trauma, drug toxicity, electrolyte disturbances, again, an MI or an infarction. Okay, so let's move on from there. Disorders of impulse conduction. Reentry. An impulse returns to stimulate tissue that was previously depolarized. Okay, so we're going to stop here. And when we come back to the next video that I'm going to make, we're going to start talking about EKGs. Okay, so from here, why don't you start working on some of your assignments on the end of the book? Maybe even start working on a little bit of your test bank. And I will be back to do another section on ECGs. Okay. I will see you soon. Thank you.